just to say something about this theorem, where there's really not that much to say, but since I promised I will anyway. So we had these two things, one generic, right? He said A forces the WE meant that there exists an initial segment of A such that this is in WE or all extensions of this thing are not in WE. Right? This is what it meant for A to force a particular CE set, and we realized that of course the CE set is a set of natural numbers, but through a reasonable coding, you can consider it to be a subset of 2 to the less than omega, and with this reasonable coding, this statement here makes sense. And so the picture you want to have is that this avoids the situation where if you have the full binary tree and say that your WE is the set of all those finite sequences sigma that have a zero. So going left is 1, going right is 0. So your WE consists of all things that contain a 0. Then you have this one infinite path here, there's one A here, which is kind of curious. Whenever you look at an initial segment of this A, you could make it into WE, but you don't. Right? That is exactly what this condition says does not happen. Right? Either if for every initial segment you can make it into the set, well then at some point you have an initial segment that is in the set, or there exists this place where you have gone out far enough such that this whole cone extending some initial segment of A is missing WE, right? So this was sort of the picture before I changed it, was your typical picture of not forcing something, where you keep being able to extend into the set, but you don't. And satisfying the jump requirements just meant that right, the eth jump requirement was the existence of an initial segment that phi sigma of E converges, or for every extension of this initial segment you have that it diverges. This was a requirement JE. And so the theorem says that being one generic, forcing all WE is the same as satisfying all jump requirements. Okay, so if you're one generic, then you in particular also force the set WH of E. So WH of E is the CE set inspired by the number E, which has to take care of the eth jump requirement. And you just look at the set of all those initial segments sigma that make that particular jump converge. And then clearly forcing this WH of E is the same as satisfying requirement JE. Not much more to say. I guess I should say H is a computable function. I actually don't even care about H being a computable function, right? If you satisfy all one generic functions, then all you need to do is find a CE set that does it. You don't have to effectively find a CE set that does it. You don't care. On the other hand, now we have something which satisfies the jump requirements, and we want to see that satisfying a jump requirement corresponds to being one generic, so we need to come up with the right function the right function is phi of ft of sigma of z is equal to 1 if there exists a stage before the length of sigma such that there exists a tau, an initial segment of sigma, such that tau is in WES and divergent otherwise. As we're looking for a function whose where the oracles, the set of oracles that make this converge needs to be this set of WEs. So, and this function, clearly, right, it ignores its input. So if the oracle is the appropriate type, then in particular, where did I put my jump here? The function on any input, in particular on the input which is its own index, has the appropriate behavior. So, and clearly this converges if there is an initial segment in WE. And so if this thing, it's hard to see what to say, right? If this thing converges on its own input, then some initial segment of sigma is appropriate. And if this thing does not converge on its own input, then no such sigma exists, and you're done. The one thing that is a little bit curious, maybe, is this part here in the definition. Right? It appears we're defining a Turing functional. Right? That's certainly my intention by writing this phi here. But a Turing functional that queries the length of its oracle. Maybe I should actually fix it to be strictly less now that I'm getting into my explanation. I realize less than a recall doesn't work so well. Right? You can't really query the length of your oracle here. So why is this still an appropriate functional?
Why can't you query the length of your oracle?
Well, because the oracle queries are of the form, is this in the oracle, is that not in the oracle? And so we have defined it with a limited sigma. As soon as you ask something which is not in its domain, then you diverge.
So I guess has to ask a bunch of different questions and
It has to answer a bunch of different questions, right? It doesn't really ask this question. First compute the length of your oracle and then start checking if there exists an S that does it. What it really does is it searches, right? It tries first S equal to 0. Now, of course, nothing converges at 0, but then it tries larger and larger values, and it keeps trying larger and larger values every time, seeing if this computation converges in the right way, until it accidentally asks an oracle question which is too big. And as soon as it asks an oracle question which is too big, the computation diverges, which exactly corresponds to the other case. Right? So this, right? We can arrange the computation so that this is exactly what happens, even though we cannot compute the length of an oracle. Because computing the length of an oracle means you need to ask a question which is outside of the domain of the oracle, and then you immediately diverge, so you can't compute it. Okay, so there isn't that much going on in the theorem, but it's kind of nice to see the one genericity corresponding to these more restrictive-looking jump requirements. So the next theorem is by itself interesting, which I don't think is true of this, right? One generality satisfying the jump requirements. Almost surely you don't care about either of these notions yet. That makes it a very difficult theorem to care about. But this next theorem is a theorem that says that, well, we know that we can jump to zero jump, right? Zero jumps to zero jump. But and we also know that any jump jumps higher than that. So the b's which are greater or equal to zero jump are the best you could hope for to jump you. And it turns out that for each such b, there exists an a such that a jump is equal to b. I left a little room open, of course, because it turns out that a jump in this particular example gets computed in a sort of interesting, curious way. A jump is equal to a join zero jump. The jump of A is the same as the join of A and zero jump. And that's sort of an interesting kind of thing that happens. But the construction will make it very clear why this happens. Okay. Everybody happy with the statement of the theorem? Right? Anything above zero jump can be jumped to. The jump is as onto as you can hope. Okay, so what do? Well, we take a set B in this degree B, and we're going to try and construct the set A that does this. So what does this set A have to do? Well, clearly, according to this second equality, A needs to be B computable. So we should do the whole construction. We're going to construct A. We're going to construct A by initial segments. And every time we go from one initial segment to a bigger initial segment, this choice of extension should be B computable, and we should make some progress. And if you do that, then we do make sure that A is less than B. And zero jump is already less than b, so then we have one inequality taken care of. So that's going to be the goal. So we make f, which is going to be a characteristic function of a by initial segments. In b computable way. Okay, not surprisingly, we start from nothing. Right? Our first approximation to the characteristic function of A is the empty function. And then we go to state s plus 1 equal to 2e plus 1. And you notice from the way we're doing these stages, there's two things we're going to try and do. The one thing we work on the odd stages, the other thing we work on the even stages, just some silly bookkeeping. So at this stage, we want to force the eth part of the jump, right? We want to decide relative to the oracle A, does the eth computation stop on its own input or not? Okay, that's easy enough. We have seen this kind of expression before. Does there exist a sigma for which there exists a t such that sigma extends our current approximation fs and phi sigma e t of e converges, right? It's exactly a question we've seen before. Does there exist an extension and a time such that this extension makes that the jump question converges? Then of course you know what follows. If the answer is yes, then we take fs plus 1 to be the least sigma that does it. If the answer is no, then we can take fs plus 1 equal to fs. Or maybe, if you want to make sure that at every single step you make progress, then you choose fs plus 1 to be fs plus an arbitrary definition at the next location. It doesn't really matter. Okay, why does this work? Right? You're trying to do things. Be computable. Well, but B is greater than the halting problem, and this question here is exactly computable in the halting problem. Therefore, B can compute it as well. So B can first of all decide if there exists such a sigma energy, and if there exists such a sigma energy, you can start your search for the least sigma in lexicographic ordering or something like that. That does it, and then you choose the least one that does it, otherwise you do nothing. Right, so far so good. So then we go to stage s plus 1 equal to 2e plus 2. So now we are at an even state associated with e. And now what we want to do, okay, so at this point we decided the jump, and if you just keep doing this, then you can see that a jump has been is computable. Right? You do the construction for the first e steps, or you do these things for the first e steps along the way, and then you know what the each jump is, if it's in there or out of there. I say each jump, but it's of course not the each jump, it's the membership of E in the jump. Each jump has a meaning as well, right? You can jump and then jump and then jump again. That's not what I'm talking about here. It's B computable, so this gives us access to a jump from B, and we can compute A from B. So the sort of, with this, the less than or equal statements seem okay. I can ruin it here, of course, but I promise you I won't. The less than or equal statements here seem okay. But we still need the jump to go far enough as well. In particular, we need B computable from a join 0 jump. How do you do that? Well, that's actually really easy. We take the length of our current approximation, so this is the first location where our approximation has not yet been defined, and then we set fs plus 1 equal to fs union n comma be. Right? This is the function that agrees everywhere with fs on its domain and is defined in one more location, and there tells you whether E is in B or not. Right? This is the ETH location of the characteristic function. So here I'm in a not very subtle way sticking B into A. Right? And so in particular, if you can decide the locations where we do this, you can compute B. Right? Oh, I should also say here, this is clearly B computable, right? Yeah. We do nothing except use one of the values of B. So this is clearly B computable. So now the whole construction is B computable. So this means that A join 0 jump is indeed less than or equal to B. These steps show that A jump is Turing computable from B, because to decide whether E is in A jump or not, you just do the construction sufficiently far and you see which choice you made over here to decide the jump. So A jump is Turing computable from B. Well, clearly, A join 0 jump is Turing computable from B. Oh, I already had observed that. Is Turing computable from A jump. If I'm not mistaken, the only thing left to observe is that B is Turing computable from A join 0 jump. Yes. As soon as we observe this last inequality, then we have all the equalities we want. And this now is completely related to the observation I made as soon as I wrote down this stage s plus 1, or the even stages. At the even stages I said, okay, we just take the value of B and we directly stick it into A, and the only thing that you need in order to now extract B from A is to be able to figure out what these locations are. Well, what are these locations? They are every time the exact next location here. This is always, we extend it always exactly by 1. So what do you then need to figure out where these locations are? Well, you need to see how far do you extend in these other stages. And these other stages, right? 0 jump computable. And we said it's 0 jump computable, therefore it's B computable, but it's 0 jump computable, therefore in particular it's 0 jump computable. So using just 0 jump, you can do these stages of the computation, of the construction, and therefore figure out where you stuck in the values of the characteristic function of B. And if you can figure out where you stuck them, then you can compute B, and therefore compute the degree of B. Everybody happy with that? Questions? Which was any inequalities that I should say something more about? Everybody happy with that? Some of you definitely do not look happy. Other construction. First observations are easy. I have a B, I'm going to construct this characteristic function. As long as I do it B computable, this one is automatically taken care of. This first inequality. Now, what am I doing B computably? Well, B computably, in particular, I'm deciding values of the jump of A. So if I'm B computably deciding these values of the jump, then I guess that A jump is B computable. Just run the construction sufficiently far out until you have decided that particular value, and then you know what that particular value is. What else? Well, this one is really the proverbial kicking in of an open door. Of course A jump is greater or equal to A, and of course A jump is greater or equal to 0 jump. So the one thing that's left over is B being computable from A and 0 jump. And then you observe that we've really, this step in many ways is clearly ridiculous. except that it works. Right? You just take the values of the characteristic function of b and you stick them into a. So clearly the values of the characteristic function of b are in a. But then you say, well, most characteristic functions have a 0 somewhere and a 1 somewhere else, so the characteristic values are always located somewhere. So the trick is that we stick these values of the characteristic functions in locations that we can zero jump computably determine. Zero jump is enough to do these steps of the construction, and if you can do these steps of the construction, then from that you can decide where these values are stored and therefore extract them. And that's exactly what this says. You can decide values of b using these two things. I'd say on average people look a little happier now. It's making me happy. Maybe I'm just wearing you down, right? Okay. So the next theorem. So here we have got a nice theorem which clearly says something deep and meaningful about the structure of the Turing degrees, which we're studying in general. And so you could wonder, okay, does any two Turing degrees have a join? Right, a join in least upper bound. Does any collection of Turing degrees have a least upper bound? This is a really nice question, which happens to have a particularly nice answer. No. Right? Why is it a nice answer anyway? Well, it's a nice answer because the theorem will prove, so this theorem shows that not every set of Turing degrees has a least upper bound, but it shows it in a very particular way, which gives us some additional information. If we have a sequence of degrees which is ascending, so the n plus first degree is Turing strictly greater than the nth degree. Right? We have here is a0, and then we have a1, and we have a2. I'm probably the only one here who gets confused by the word ascending, because it somehow doesn't. It's a perfectly normal English word, but somehow it doesn't really work in my brain. Anyway, so you have this strictly increasing sequence of Turing degrees. And so whenever you have such a sequence, this has an exact pair. Meaningless theorem until I give you the definition of an exact pair. An exact pair for such a sequence is a pair of degrees b and c, such that that's not a very good definition. I'll give the corrected definition. We have b and c. They're both above everything in the sequence. So both of them are upper bounds for the sequence. So this is for every n, a n is less than or equal to b and c. So far nothing nice happened. But now for every degree d, if d is less than both b and d is less than or equal to c, then there exists an n such that D is less than or equal to AN. That's exactly. So whenever you have something, a single degree, which is below both of these, right, then there exists an A which is above it. Right? And it says an A greater or equal to it, but then of course A n plus 1 is strictly above it. Right? It's a strictly increasing sequence, so if you're below something in the sequence, then you're strictly below the next thing in the sequence. So you have two upper bounds, but there's clearly no least upper bound, because the least upper bound for the sequence would be such a D, but it would also have to be greater or equal to the elements in the sequence. So this is exactly the picture. Could have put it a little bit more spacious, but everybody happy with the definition? Right? An exact pair, two upper bounds, such that anything below both of these upper bounds is already below a member of the sequence. Yes?
Do you want strict inequality for D between B and C?
No, I don't think so. Here you mean?
Yeah.
Otherwise the chain would end. D was equal to B, and B and C are equal. Because B is then less than or equal to C, so the chain would at some point end with like B or something. B can equal C.
Yeah.
Oh, okay.
It follows, I believe. Is what you're saying.
Yeah.
It follows, because suppose it's equal to B,
Right, no, I got it.
then okay. So how do we do this? Well, first of all, you can wonder, okay, you have this increasing sequence, and is there anything at all above it? Because if there's nothing above it, then in particular it's very difficult to construct an exact pair. But this works out pretty easily. You've already seen most of the ideas. So choose AN to be, right, a representative of AN, and then we can choose the set A to be the set of M such that M is in AN. Right? This is exactly the same idea as the join of two sets, except that you're now joining together infinitely many sets. And the idea or the picture you should have is really that you take natural numbers times natural numbers, the plane, and in the end column you stick in exactly set AN. Right? So you collect all of these sets together, and now clearly you get a set of natural numbers, and also it's very easy to compute AN from A, because to decide membership of M in AN, you just look at the end element in the end column, and the answer is exactly derived. So this A here, or I guess the degree of A is an upper bound. Okay. Well, what do we want to do? Well, right, B and C we want to be upper bounds. And so, how do you now construct, using the fact that A is an upper bound, how do you construct another upper bound? Well, the observation is, or the basic part of the observation is one that we've made many times. If I compute something, if I can compute something using an oracle, then I can also compute that same thing with any finite modification of the oracle. Right? Finite modifications never change anything essential in our context. So in particular, right, an is Turing reducible to A. Well, it's really Turing reducible to the nth column of A. So as long as I construct a set B such that for every n, the nth column of B is almost exactly equal to the nth column of A. Right? If in every column I make only finitely many modifications, then for the computation of an, I just have something which is finitely different, and therefore this nth column of B also computes this at an. And of course then the same for C, where I didn't say it, but of course B is a set whose degree is going to be B, and C is a set whose degree is going to be C.
The start of the last equation.
Yes. Otherwise, the theorem is in trouble, right? Almost everywhere equal is transitive in particular. So this means that what we want to do is satisfy, right? I can now write down some requirements. The thickness requirement for B says that the wide column of B is almost equal to the wide column of A, and the thickness requirement for C is that the wide column of C is almost equal to the wide column of A. And if I satisfy all thickness requirements, and thickness means, right? It means exactly this, almost everywhere equal. And of course, A and B are certainly going to be infinitely much different. Well, let me say, B and C are certainly going to be infinitely much different, because otherwise they compute the same kind of things, and this would be immediately false. So at least one of B and C is infinitely much different from A. But per column, it's restricted. That is the thickness trick.
We should make sure B and C aren't the same too, right? In the requirements.
Yes. So this thickness requirement takes care of the upper boundness. Now I need to come up with another requirement. I'm just trying to check whether there's something else I want to say about the thickness requirements before going on to the next set of requirements. And I don't think so. Okay, thickness requirements. So now, of course, in good style, we know. So you decide on requirements, and then you figure out a basic module, and then afterwards you try and see if the basic modules combine. Now, the basic module here is, of course, very easy. At the wide step or something like that, you have the wide column of B not too determined yet, and then at this step you say, okay, now the rest of the wide column of B is exactly like the rest of the wide column of A. So our construction is going to go on by every now and then defining B and C on whole columns, while ensuring that sticking out of these columns we have only a finite part. Because if we do that, then this basic module works. We have only a finite part here. So at the next step, we can define the next column here. It's exactly the same as A, well, except in this earlier part, which we had already determined, that earlier part being finite, takes care of the thickness requirements. So, that's good. We have requirements to show it's an upper bound, and we know how to take care of them. And what restriction this imposes on us. So now we just need to figure out. How to take care of the exactness of the pair. Right? The last part. Well, now if you just write down the requirement that clearly says the exactness, then we can figure out what goes on. So what is the requirement that clearly says the exactness? The requirement says if Turing functional E and Turing functional I compute the same thing from B respectively C, then that same thing should already be computable from some AN. That is to say, if phi E of B is equal to phi I of C is total, right? If it's not total, then in particular it's not a characteristic function of a set. So whenever these two things agree and are total, then it should be the case that there exists a Y such that phi E of B is Turing reducible to a Y. I don't know why I call it a Y, it should clearly be an N. This requirement, if we can satisfy it, it clearly works. Now also, you look at it and notice that this is the type of requirement we've thought about before. How did we satisfy this type of requirement before? Well, we said we have some approximation of B already, we have some approximation of C already, and now we're going to look if there exists an input X and if there exist extensions of our current approximations that compute different values. That was our general strategy for doing some requirement like this. Look for an extension of what we currently have for B and an extension of what we currently have for C, such that they compute different values. If these extensions exist, then we choose these extensions and we have made these things different. If these extensions don't exist, then this should happen. Okay, let's see that this happens. Now, we have a little difficulty, because along the way we took care of our thickness requirements, so it is no longer the case that our current extension to B and our current extension to C are finite. Yes, they are infinite. But how are they infinite? They are infinite in exactly that there is a bunch of columns determined, and then a finite part sticking out. What can we ask? Well, we can certainly ask the question, does there exist a sigma? Does there exist a tau? Does there exist an x and a t such that sigma is compatible with sigma s, which means that, right, sigma, we're doing here a search. This should be a search through the natural numbers, so we can search through infinite things, but we're looking for a finite part of a characteristic function that agrees wherever sigma s is defined with sigma s. Sigma s is our current approximation to the characteristic function of B, I guess. Right? So we're looking for some finite function that is compatible with what we currently have decided for B. And we're looking for something which is compatible with what we currently have defined for S, such that phi sigma E of T of X converges but is different than phi tau E of T Q should clearly be an I. Which one is the I? C is the I, so this should be an I here. Do there exist these values where they are different? Right? And if these computations converge, then in particular you ask only finitely many oracle questions. So you know that the sigma and the tau you're looking for really only have to be finite. It also matters because now, of course, if the answer is no, well, we'll analyze in a moment, but if the answer is yes, there exists such sigma and tau, then of course I want to say sigma s plus 1 is equal to sigma s union sigma, and tau s plus 1 is equal to tau s union tau. So we extend our current approximations in such a way that these computations end up different. And in that case, we won, right? We took care of the requirement, it's taken care of. In the other case, if such sigma and tau do not exist, then we need to win in the other way. How do you win in the other way? Well, instead of making the hypothesis false, you maybe want to try and make the conclusion true. So then you should be computable from AN. Well, you're not computable from AN so much as you are computable from the first n columns of A. Right? AN is an upper bound to the first n columns, so being computable from the first n columns of A is good enough. So why are you indeed computable from the first n columns of A if the answer to this question is no? Right? There do not exist such sigma and tau? Well, either because you might just never be total. Right? If you're never total, then it's an automatic way. If you are, however, total for some choices of B or C, then you can just do this search. Right? If you are total, for in particular the B and the C you end up with, then in particular there exists sigma and tau. In particular, for every x there exists sigma and tau which compute this, but it doesn't depend, the value doesn't depend on your choice of sigma or tau. So then you do exactly also what we did before, and that is to say, to compute this from the first n columns of A, you do this search and you just look for the lexicographically least sigma where this value is defined, and that is the value of the function you computed in the end. And therefore you compute it from the first n columns. Now I lied a little bit, because you don't really have the exact first n columns of A. You have the first n columns which have been messed up finitely much, but right, finitely much doesn't really make a difference. So that works out just fine. End of proof.